Welcome to the Explainer. Today, we're not just going to talk about calculus, we're going to build a powerful toolkit. By the end of this, you'll be able to look at pretty much any graph and see the story it's telling. You'll see its peaks, its valleys, and all the hidden patterns. So let's get right into it. So here's our game plan for today. We're going to start with the most basic, most fundamental tool in our kit, the derivative itself. Then we'll start adding layers, right? We'll bring in the first and second derivatives to see what clues they give us. After that, we'll put all these new tools to the test with a real-world problem. And then finally, we'll take a step back and just admire the awesome toolkit we've built together.
Okay, first things first. Let's talk about the cornerstone of this whole thing, the derivative. What in the world is it, and, why is it so important?
Okay, so you can think of the derivative as kind of like a magnifying glass for change. It lets us zoom in on one single, precise moment in time and see exactly how fast something is changing right then and there. On a graph, that's just the steepness, the slope of the curve at that one spot. The speedometer analogy is absolutely perfect. If your function represents a journey, then the derivative is your speedometer. It's not giving you your average speed over the whole trip. Nope. It's telling you your exact speed right now at this very second. It's the difference between saying the trip took an hour and knowing you were going 65 miles per hour the exact moment you passed that speed camera. See the difference?
All right, so we've got our first tool. Now let's see what it can actually do for us. The first derivative, which we write as f prime of x, is basically a compass for our function. It tells us exactly which way the function is headed.
And the coolest part is, the sign of the derivative gives us a really simple but powerful clue. If it's positive, our function is going up. Think of a stock price climbing. If it's negative, the function is going down, like a company's profits falling. It's that simple, uphill or downhill.
So, okay, we get uphill, we get downhill. But what about those moments in between? What happens when the path just levels out, even for just a split second? Well, this is where things get really, really interesting.
Because when that derivative hits exactly zero, we found what's called a critical point. This is where the function is momentarily flat, and that signals a potential peak, what we call a local maximum, or a valley, a local minimum. These are the turning points, and finding them is absolutely key to understanding the big picture of any function.
Okay, our toolkit is getting bigger. Now we're going to add a new tool. This one goes beyond just direction. It actually helps us understand the very shape of the curve itself. This is where we start seeing the subtle details, the curves and bends that tell the full story.
So meet the second derivative, or f double prime of x. If the first derivative was your speed, then the second derivative is your acceleration. It tells you not just how fast you're going, but if you're speeding up or slowing down. It's the rate of change of the rate of change. Kind of meta, right?
And this is just a brilliant way to visualize it. When the second derivative is positive, the curve is concave up. Just think of it like a bowl or a cup that can hold water. But when it's negative, it's concave down, like a dome or a cap that would spill water. It's a super simple visual cue that tells us everything about the curve's shape.
Okay, so we've got curves that hold water and curves that spill water. But what about that exact point where it flips from one to the other? What do we call that moment of change?
That special spot is called a point of inflection. It's where the curvature switches, and we can find it by figuring out exactly where the second derivative equals zero. It's another one of those crucial landmarks on the map of our function.
All right, we've got our tools, we've assembled the kit. Now let's get our hands dirty and put it to the test with a real-world problem. This is where all that theory becomes practice.
So this is a classic problem. It's the kind of thing engineers and businesses deal with all the time. We've got a target volume we need to hit, but we want to build this thing using the least amount of material possible because, material costs money. We're trying to minimize our costs while still meeting our goal. And here is where our toolkit just completely shines. First, we set up a function for the thing we want to minimize, the surface area. Then we pull out our first tool, the derivative, to find its rate of change. We set that derivative to zero. Why? Because that finds us the critical point, the spot where material use is at its lowest. A little bit of algebra later, and boom, we have our answer. A width of 3 meters gives us the most efficient design. It's just an amazing example of how calculus solves very real problems. So let's just step back for a second and admire the toolkit that we've put together. It's so much more than just a bunch of formulas. It's a whole new way of seeing and understanding the world. Think about it.
With the first derivative, you know the direction. Is it going up or down? You can find the exact peaks and valleys. Then you bring in the second derivative, and suddenly you understand the shape. Is it curving up or curving down? And you can even find those subtle points where the shape changes. Altogether, these tools give you a complete, detailed picture of how any function behaves.
You know, this quote just perfectly captures what we've been doing here. This whole thing, it's not really about just crunching numbers. It's about developing a deeper feel and intuition for how things change. It's about getting the why behind the what. And really, this is just the beginning for you. From economics to physics, from business to biology, the ideas we've talked about today are literally everywhere. With this toolkit in your back pocket, you now have the power to analyze, to understand, and even to predict the world around you. So, the only question left is, what are you going to explore first?